Hi, and welcome to Learning 3D Character Animation with Jeff Lew. I'm Jeff Lew, and let me tell you a little bit about myself. I'm a self-taught animator, and I've been working in the CG industry since 1997. Before that, it took me about 1 to 2 years of full-time studying and practicing on my own before I got my first full-time job doing 3D animation. Hopefully this DVD will help you get to that level much faster than I did. I fell in love with 3D character animation the moment I started doing it. I couldn't believe the power and flexibility of CG. You can create something out of nothing. You can turn your ideas into something others can watch and enjoy. So what does it mean to be an animator in the CG industry? Well, you must never stop being a student. You can never stop learning. This industry and technology moves so fast that if you don't keep up, you'll be left behind. The ones who persevere and keep working at their craft will be successful. 3D character animation is twofold. On one side, you have the artistic ability. On the other side, you have technical proficiency. This DVD focuses on the practices and principles in creating good character animation. You will develop faster and be more disciplined in your craft if you have an understanding of how things work and the reasons behind each principle. It's a long road, but I hope this DVD will somehow inspire you and support your quest in becoming a character animator. Before we start talking about animation, let's talk about the world space. The world space is the virtual world in which your 3D characters would exist. It has 3 dimensions. The first dimension is the x-axis. If you're looking directly at your screen, x runs from 0 to positive infinity or 0 to negative infinity going across your screen. And depending on your units, could be centimeters, inches, feet, or whatever, wherever you are on this axis would give you a value of like positive 15 inches or negative 35 feet. But you can never leave that one dimension. Let's bring in a second dimension. Now the y-axis goes straight up or straight down. Positive going up, negative going down. And combining x and y, it'll give you this plane. So if you go 5 units in x and maybe 10 units up in y, you're going to be over here. It's going to be that coordinate. But you can never leave this plane. That's where the z-axis comes in. Z is the depth. If x is going across, y is going up and down, z is going to go straight towards you and straight behind me. Positive towards you, negative behind me. Now instead of a plane, it creates a volume now. So instead of this plane, you could be over here or you could be back here. You could be in any one point in this world now, but that will give you a value of x, y, and z. Okay, that's how the 3D software keeps track of where your object is at any one point in time. It's very important to know this coordinate system because computer animation is very mathematical based. Now fortunately, we don't need to know the math behind the animation. The computer does that for you, but it's very important for us to know which way is positive y, which way is negative z, or positive x, because the tools you'll be using later on would depend on the fact that you know which direction is which. Computer animation differs from traditional animation and claymation in terms of world space, because in traditional animation you draw your figure on a piece of paper, and that's a very relative world space. In claymation, you animate the figure in front of you on the table or the stage, and that's a very relative world space also. In computer animation, your world space is infinite, going from the center of your world at 0, 0, 0 to any infinite direction. So say at 1 second, your object could be in this point in time, and 5 seconds later, your object could be over here. So going a course of 5 seconds, your computer will interpolate for you going from this coordinate to this coordinate. And that's a very simple animation. But as your animations get more complex, you'll realize the importance of knowing what the world space is. Picture this. There's a person standing in the center of the world space at 0, 0, 0 for x, y, and z. And in the palm of his hand is a little bug. Now, to this bug, this hand is the entire world. The bug knows nothing outside of this hand. So to him, he's in the center of his own world at 0, 0, 0. Now, say the person takes 10 steps forward and then 10 steps to the right. Now, his position is 10, 0, 10. What is the position of this bug? Well, he still thinks that he's in the center of his own world. So he thinks he's at 0, 0, 0, and that's his local position, dealing with this local world. His global position is going to be the same as the person, pretty much 10, 0, 10. And that's the difference between local position relative to this local world and global position, which is relative to the entire world space. This happens when two or more objects are in the same hierarchy. We call one object the parent and the other the child. Now, it's not taken in a literal sense where this person gave birth to this bug, but it's more of a way for us to define the status level of these 3D objects. A child is any object that is below another object in the same hierarchy. A child's motion will always be affected by the parent's motion. A parent's motion will never be affected by the child's motion. Try to think of it in terms of something like a kangaroo, where the parent is carrying around a child in its pouch. So wherever this parent went, this child had to go. But the child was freely able to move about inside this pouch, and it didn't care where the mom went, and it was pretty much oblivious to where the mom's going. But wherever he moved inside the pouch would be his position, would be the position in which he thinks that he is in. Now, a hierarchy could be more than two objects. It could be 3, it could be 10, or it could be 2 billion objects. And each child doesn't have to have another child. Each child can have a sister-like person, which is in the same level as this other child, this sibling. Say we have one parent. It can have 2 children that are in the same level in the hierarchy. So if you move one child, the other child's not going to move, unless you put this third child underneath the second child. Now, the third child becomes the child of the second. So now the second becomes the parent of this third. Let's describe it in terms of color-coded balls for easier understanding. Say we have a green ball, a blue ball, and a yellow ball. We put the blue ball underneath the green ball. So now the blue ball is a child of this green ball. And now we put the yellow ball underneath the blue ball. So now the yellow ball is the child of this blue ball. If we move the green ball, both the blue ball and the yellow ball move along with it. If we move the blue ball, only the yellow one moves, and the green ball is not affected, because the blue ball is one lower in the hierarchy than the green ball. If we move the yellow ball, nothing else moves with it, because the yellow ball has no child, and the blue ball and the green ball are both parents of this yellow ball. So let's rearrange this hierarchy. Let's take the yellow ball out of the blue ball and place the yellow ball underneath the green ball. So what do we have now? We have the blue ball and the yellow ball being in the same level in the hierarchy. If we move the green ball, again, both the blue ball and the yellow ball move. But if we move the blue ball now, only the blue ball moves because it has no child. And if we move the yellow ball, only the yellow ball moves because it has no child. And the blue ball and yellow ball pretty much are independent now. They're both children of this green ball, but they have nothing to do with each other. Now, there's a name for this green ball. The green ball, no matter what configuration we do, as long as the green ball is the top parent, if it's the top object or top node, it's called the root. So wherever we translate this root, everything else has to go. And this green ball will always be the root unless we put this underneath another object. Then that object becomes the root. So a root has no parent. Anything in 3D can pretty much have this parent-child relationship. You can have 2 empty null sets or 2 locators be parent or child, or you can have 2 models be a parent and child, or you can mix it up. You can have a bone being the parent and a model as a child, or vice versa, or however you want. Now, in terms of character animation, we're going to talk in terms of bones. So let's take an arm, for example. We're going to divide it up into 3 bones. We're going to divide it into the upper arm, the lower arm, and the hand. If we move this hand and we don't move this lower arm and upper arm, there's nothing that's going to happen to this lower arm or upper arm, because this hand is the lowest node in the hierarchy. It's the lowest child. It has no effect for this part or this part, because these are both parents of this hand. Now, if we animate the lower arm, it's going to have an effect on this hand because this hand is a child of this lower arm. So wherever this arm moves, this hand has to go with it. And it's going to have its own independent little twiddling animation around. Again, the upper arm is not affected because it's the parent of these children. Now, if we move the upper arm around, it's going to affect everything down below it. It's going to affect the lower arm, it's going to affect the hand. And in our case, in this three-joint object, this upper arm is the root. Wherever we translate it, whatever we do to it, it will affect also all the children underneath it. If we now look at the entire body, it's usually the hip joint that is the root for the entire character. So that means when you want to translate the entire character around, you usually grab the hip joint. And all bones are in some way connected to those hips. Going up from the hips is the spine, then splitting off to the two arms and going up the neck and the head. And also going down from the hips are the two legs. If you look at the two legs in a hierarchy, they should be in the same level in a hierarchy. And if you look at the two arms, they should be in the same level in a hierarchy also. So that means that you can animate one arm independently from the other and one leg independently from the other. Since we're talking about the entire skeleton, the next topic is going to be character setup. And we need to do this because without a character, we can't character animate. So bear with me, all right? Character setup is a very in-depth topic, and it deserves its own training video all on its own. But it's very important for a character animator to know character setup, because when you're animating a shot and you find that it's very hard to animate a certain move or a certain thing that this character has to do, sometimes it's easier to adjust the character rig than animating the hard way. Now, before you set up a character, you have to look at what your character looks like, what your character is going to be doing in the animation. Is your character a cartoony character or is he photoreal? It all depends on these questions, what the skeleton will look like inside his body. The method of character setup is different in every software package, but the idea is the same. The basic idea is that you have a 3D model of a character and you insert a skeleton inside to control this 3D mesh. So for example, if I have an arm and I insert some bones in the arm, then I assign some of the polygons or some of the NURBS control points or the spline control points to this bone in the arm. Wherever I move this arm, those points will follow. You would do that for the entire skeleton, so whatever limb you move, those points on the mesh should follow that limb. You can always tell when a certain point in the mesh does not belong to any bone when you drag the entire body around and you see certain points sticking out like spikes. That tells you that these points don't belong to anything and you want to reassign those points to whatever bone they're supposed to belong to. Now, the skeleton shouldn't be anatomically correct. If you're setting up a skeleton for a humanoid character, there's no way it should be anatomically correct in terms of the amount of bones because there's just so many bones in the body. We want to keep things simple because in animation, if we have fewer bones, that's fewer bones to pose. If we have 100 bones to pose, on each keyframe, we're going to have to rotate 100 bones. And that's not too fun. To have a fun animation, the fewer the bones, the faster you can animate. But you should be careful about having too few bones. You should have enough that you can deform your character to look anatomically correct. Now that's the key. You want your character to look anatomically correct, but you don't want the underlying skeleton to be anatomically correct. The things you got to look out for are where the joints are positioned in the body. So you want to be able to rotate your limbs in the correct manner. You don't want to have an elbow joint over here. You want to have it over here. Looking at the spine, there's a lot of vertebrae in the spine, and we don't want every single one in our character. I usually like 3 to 4 bones in a skeletal spine. I believe 4 gives you more than enough. 3 is pretty good also. You just want enough that you can easily bend your character and make him look flexible without creasing your model in any way that it's not built for. If you look at a human spine, if you look at in any textbook, you'll see that the spine is curved, like an S curve. You don't want to set up your bones in that manner. The reason for that is because when you do a twisting action with your bones, if your bone is angled like this, if you have an S-curved spine, Rotating it in this axis is going to rotate your chest at an angle, and that's not natural. You want to have a spine that's more straight. So when you rotate your chest, it's going to rotate the way you want it to. It's going to look anatomically correct, but it's not really anatomically correct. Now, talking about some other joints, the biggest problem usually for characters in 3D are the shoulders, because the amount of rotation that you need in your character is very difficult to get in 3D. In a human, it's a ball and socket joint. It's very articulate. You can move this like crazy. You can move it anywhere you want. In 3D, the bones are really pulling the points on that model. So if you have any twisting motion, it's not really the skin sliding over the muscles. It's really the bone directly controlling the skin. It's going to give you pinching. Sometimes, if you can avoid that complex shoulder, the better. If you can design your character with, say, detachable arms, maybe give him armor or some sort of shirt where he can twist any way he wants and you don't really see it. You don't really see the error in that shoulder. Another solution for the shoulder area is to split off joints. This is another case where a character is not anatomically correct. If you look at the arm, usually we have one joint going from here to here and another joint going from here to here. But if you wanted to avoid this pinching problem that you get usually in the shoulders, we can add a joint in the middle. So have a joint going from here to here and then here to here. So this joint will take care of this type of rotation, and then this joint will take care of this rotation and this rotation. And that's one way in 3D how we can avoid known problems. Another case where you might not want to be anatomically correct is when you want to add certain bones to do certain functions. Say you have a character that likes to spin around, that likes to jump up in the air and do somersaults and flips and crazy spins. You might want to add a bone for the center of gravity, for the character to spin around that center of gravity. What we talked about before, having the hips as the root, if you rotate around that root doing a somersault, that doesn't look correct in terms of spinning around the center of gravity, because a character's hips might be pretty low, especially if your character has short legs. If you're going to rotate around his hips, it's going to look lopsided. So if we have another bone for the center of gravity, that character can spin and rotate around this center of gravity bone, and placing that pretty much where the center of gravity is for that character, and it can have natural spins and twists and whatever. Now that means the hips are no longer the root for that character. This center of gravity bone is. And that's very tricky. The more bones you add, the more you have to worry about. Now the key for a character setup is to keep your character setup simple. So when you're animating your character, it's going to be easy, it's going to be fun, and you're not going to get too burnt out from animating, because the more bones you have, the more things you got to keep track of, and the less fun it gets. It becomes pretty tedious. But keeping a character simple doesn't mean to have as few bones as possible. You can have a very complex setup, but you can also have very few controls to animate that character. One case of a complex setup making your life a lot easier might be in the hand. If you look at the hand, there's just so many joints you have to worry about, and animating each joint in each finger is going to be very tedious. So if you know in your animation that you just want the hand to be open and closed in a fist, you can make a slider. So for example, the slider at 0 could be a closed fist. If the slider slides to 100, it'll open up the hand. Slide back to 0, it'll be closed. Now this is another case of making your life a lot simpler with a very complex setup. Actually, setup's not that complex. This is something you'll learn later on when we get more into detail about the animation principles. If you've already been animating, you're probably running into a problem where your feet go through the floor or your hands penetrate through something you want to hold on to, like a table or a cup or something like that. There's a feature in most software packages. Almost any character animation package should have a feature called inverse kinematics. Now, what we've been talking about before is called forward kinematics, where, say you rotate the shoulder, then you rotate the elbow, then you rotate the hand. Now, that's in a very forward direction, going from the top of the hierarchy down to the bottom of the hierarchy. In inverse kinematics, we can grab the hand and move it anywhere we want, and it's going to solve for this elbow and this upper arm to be in the position so that this hand is where we want it to be. So we could pull this over here, and these joints are going to solve. We could pull it down here, and these joints are going to solve. Now, there are many functions of inverse kinematics, but the main function is to keep limbs from penetrating or going through objects that you don't want them to go through. So the feet will stick to the floor, your hands will stick to the steering wheel, and so on. Another advantage of IK over forward K is that you have only one point to animate. You have this target, so you can translate this anywhere you want, and all these joints will be positioned to that target. In forward K, you have all these joints you need to animate now. That might be like 3 more things you have to animate over this one target. One disadvantage about IK is that if you happen to pull the target out too far for the limbs to reach, those limbs will snap pretty quickly, and that'll give you unnatural motion also. So you have to be aware of how far you pull your IK target, because the bones will not stretch. So be wary of how far you pull your IK chain so your limb doesn't overextend so quickly. Now, the greatest problem in inverse kinematics is you lose the natural look of the limb. So in forward kinematics, when we rotate, we get a natural arc. So if I rotate my shoulder and elbow, I get a natural looking arc, like I'm picking up something. With inverse kinematics, since everything is controlled by this end of the hierarchy, when we translate, we're no longer getting arcing type motions. We're getting linear type motions. If I translate my hand from here to here, it's going to be linear looking, and that's very robotic. It's not very organic looking. So that's the trade-off between forward kinematics and inverse kinematics. Now, you have to pick and choose what you want to best fit your shot. If you're going to be grabbing a lot of things, like if your character is going to be picking up lots of things or running all over the place, definitely use inverse kinematics. If your character is going to be flipping in the air, doing crazy spinning kicks, or just not touching anything with his hands, forward kinematics might be the better way to go. So probably the best setup would be a hybrid type setup where you can switch from IK to forward K pretty easily. Because in most cases, your character is going to be doing more than just walking and more than just flying in the air. He's going to be doing both. And you want to be able to switch from IK to forward K easily. Sometimes it's just a switch turning on IK when you need it and turning it off when you don't need it. Sometimes it's another slider type deal where you can smoothly blend from IK to forward K. And that's often the best because switching on and off IK, you usually see a popping motion. Say my foot is on the ground or my hand is on the table and I switch to IK once I get to that table, you're going to notice a simple little jitter, little glitch there if you're not careful about posing your forward K and IK at the same position. So using a slider type deal to blend from IK to forward K over a large number of frames, you'll get a less noticeable type of switch. The important thing is that you know the difference between IK and forward K and when to use them. For example, I usually like using forward K in the arms because I like to get that free-flowing rotational look to them. And I like using IK on the feet simply because it's easier to keep the feet from going through the floor. Another very important feature in character animation is the constraint system. Now, not all character animation software has constraints, but if your software does have constraints, that's a very good thing. Now, don't confuse constraints with rotation limits. For example, a limit would be where one joint can't move further than a certain rotation. Like my elbow cannot bend further than this. That's a limit. A constraint is a way to force one object to do what you want it to do at all times, no matter what. Some of the important constraints are things like the translation constraint or point constraint. Now, this constraint forces one object to be translated to the position of another object. For example, if I translate this blue ball to the green ball, wherever I move this green ball, this blue ball has to go. Now, this doesn't mean however I rotate this green ball, this blue ball will rotate. That's not the case. This is only translation. So if I rotate this green ball, nothing happens to this blue ball. Now, where would you use this translation constraint? Say you have a character who needs to jump in a car and drive around and then jump out of a car. Well, in the old days, before constraints, we would have 3 different models for this. We would have the character, the car, and a model of the character in the car. So you would do this by animating the character to hop in the car, then turn off the character and turn off the car, and then turn on the model of the character already in the car. And when you move them around, it's just one model, so of course it looks like the character's in the car. Now, there's nothing really wrong with this, but it's an old way of doing things, and especially nowadays, it's going to affect things like special effects that you add to your character or motion blur for that scene, because on that instant, there's not going to be any motion blur. It also makes your scene bigger, and it's harder to organize that way. So with the translation constraint, you can constrain your character to the car and then just move the car around, and the character will move with the car. When you want the character to get out of the car, just lower the enforcement of the translation constraint down to 0. And now your character and car can move freely by themselves. Pretty much in conjunction with the translation constraint, there is an orientation constraint or a rotation constraint. Now what that does is, say I have a blue cone and a green cone. If I orient constraint this blue cone to this green cone, it doesn't move anywhere. It doesn't translate anywhere. But if I rotate this green cone, this blue cone will rotate just like it. Now, where would you use this? Well, for characters, most of them have 2 eyeballs. And in the theme of keeping things simple, say you just want to animate 1 eyeball. So you can orient constraint the other eyeball to this 1 eyeball that you're rotating, and that's one thing to animate now, just that 1 eyeball. You don't have to animate 2 eyeballs anymore. And you can be sure that wherever this eyeball is looking, the other one's going to be rotating just like it. You can also use these 2 constraints when picking up objects. Say you have a character such as a bean who's going to pick up a gun. Now you would need to use 2 constraints. You would need to use a translation constraint to translate this gun to that bean's hand. And then you would need to orient constraint to orient that gun to follow the rotation of the hand. So the gun looks totally like it's in this bean's hand. The third important constraint is the aim constraint, and it pretty much does what it says. It forces one object to aim at something else at all times. So say I have a blue cone that's aim constraint to a green cone. Now you're going to see that this blue cone is going to point to this green cone no matter where I move this green cone. Now where would you use this aim constraint? Well, in character animation, let's go back to the eyeball animation we were doing, where the right eye was orient constraint to the left eye. Now say we had a scene where a character needed to look at certain objects on a table, and we wanted to make sure that he was really looking at these objects. Well, instead of guessing where these eyes are going to be looking by just rotating and estimating, we can tell it exactly where it should look by aim constraining the eye to a certain null or locator. So wherever we translate this locator, the eyes are looking exactly at that spot. Now there's other constraints like scale constraints or surface constraints or tangent constraints, things like that. They're not very widely used. Well, for example, surface constraints might be used for keeping objects on the surface of a model, maybe a teardrop or a sweat rolling down someone's cheek. Now the constraints I talked about earlier are very important in character setup because they can make your character setups very complex yet much easier to animate. For example, in IK, where it's kind of difficult sometimes to adjust the position of the elbow. Maybe it's erratic, it's random sometimes. So if you aim constraint your arm to point at a certain object, then it's easy to aim where this elbow is going to be at. And the same goes for the knees, to aim where the knee is supposed to point at all times. Also, going back to that walking animation with the head, maybe you can aim constraint the chest. So the head can look somewhere and the chest can move about wherever it wants. This is a sort of isolation type setup where different parts of the body are isolated from the other parts. So you don't have to really do everything in forward kinematics where the chest would affect the head. If you rotate the chest, the head has to rotate. This is no longer the case. You can aim the head and rotate the chest anywhere you want. And that makes life easier sometimes. Sometimes it makes it harder. It's up to you to experience these different tools so you know which ones to use on which animations. Another key thing about constraints is that it turns your rotational data into translational data. Let's go back to that eye animation. Instead of rotating the eyes, you're now translating this locator for where the eyes should be looking. It's much easier to look at translational data than rotational data because translational data deals with the axes we're used to, like the X, Y, and Z. Rotational data is somewhat more difficult because it's a combination of X, Y, or Z rotations. Now this is something we'll go into next using the graph editor. Now we're going to talk about the graph editor, which is sometimes called the curve editor. Now what the graph editor does is that it gives you a graphical representation of your motion curve by plotting out the data points. Now the graph editor is one of the most important tools in character animation, so pay very careful attention because you will live in the graph editor. Looking at the graph editor, it looks like any old type of graph. Going across the horizontal axis is the time value. Now, time could be measured in time code or frames. Animators usually like frames better because it's much easier to read. Time code is pretty difficult to read in terms of animation. Going up and down the vertical axis is the value of your selected object. Now, the value could be in terms of translation, rotation, scale, percentage of the constraint, or whether it's on or off. Any attribute that you select that is animatable. Now the easiest thing to look at first is the Y translation, because looking at the curve that it plots is pretty much what your object is doing. Let's take a ball for example, and let's keyframe this ball at a height of 0 for frame 0. And at frame 10, let's move this ball up to 20 units and keyframe it there. At frame 20, let's move this ball back down to 0 and keyframe it there. If we look at our graph editor, we can see the curve that our motion is giving us, and it pretty much looks like a parabola. If we go back to our animation and at frame 30 we can keyframe this ball at -20, and in frame 40 we can keyframe this ball at 0 again. And if we go back to our graph editor, we can see what the curve looks like now. Now if you look at the curve itself, you can see that it's very smooth at the apexes of its curve. Now why is that? It's because by default your software should choose a spline interpolation for your animation. Now there's many different types of interpolation. We can have a spline interpolation, which we have right now. We can have a linear interpolation, or we can have a step interpolation. They will all give you different types of motion. Now if we look at our animation with this spline interpolation, we can see that it gives us very natural looking motion, where this ball goes up and when it reaches frame 10 it slows down and starts going down, and then when it reaches frame 30 it slows down and then starts going back up until frame 40. Now this is very natural looking motion. It gives us acceleration and deceleration. If we switch our curve to be linear, then watch the difference. Our ball would go up at a constant rate, and then it'll look like it'll hit some hard ceiling, then go down at a constant rate and look like it's going to hit a hard floor. Now this motion is very linear and very constant. There's no acceleration, there's no deceleration. It's very mechanical. If we switch our curve to be step, watch what happens. Our ball stays put for about 10 frames, then pops up to the keyframe for about 10 frames, then jumps back down for another 10 frames. There's no interpolation. It's pretty much on or off. Let's try a different type of animation. Let's delete this animation and let's keyframe our ball at frame 0 at height 0, and let's go to frame 10 and keyframe our ball at 10 units up, and let's go to frame 20 and then keyframe our ball 10 more units up. If we play this animation, we can see that this ball will rise constantly from 0 to 20, and in our graph editor it'll show us a straight line giving us constant velocity. Now, there's another important feature in the graph editor where you can control the tangents of a curve. So let's look back in the graph editor and select the keyframe at frame 10, and we can see some handles pop up. Now these handles are the tangent handles. If we pull at these handles, we can see that we can adjust the curve. We can adjust the curve to whatever we want. First, there's an option for letting us flatten out this tangent. So if we click that option, our tangent will be flat. Now if we go back to our animation and play our animation through, we can see that our ball will decelerate by the time it gets to frame 10, pause there for a certain bit, and then accelerate back up and go onwards to frame 20. By flattening out a tangent, that's a good way to show ease out and ease in, and that's another principle of animation that we'll talk about later. We also have the ability to stretch out this tangent to as far as we want or as little as we want. So let's say we stretch it out even farther. So what's the effect? Now by looking at this curve, let's try to figure out what's going to happen to this ball before we look at the animation. If we look at the slope of this curve in the beginning, it's pretty steep. It's much steeper than before. So it's going to change its value from 0 to 10 much quicker in a less amount of frames. So the ball is going to shoot up much faster. And if we see the keyframe at frame 10, the value does not change for a longer period of time. So that ball is going to sit there for a little bit longer. And continuing more, we see that the slope of the curve is steep again for a shorter amount of time. So that ball is going to shoot up much quicker. And looking back at our animation and playing it through, that's exactly what happens. If we go back to the graph editor and look at the keyframe at frame 10, let's do another function of the graph editor. Let's break the tangent. We can now click this button and break the tangent. So what that means is we can pull each handle of the tangent independently of the other, and we can create our own type of motion curve. And as you can see, if we break our tangent and make it into a shape of a V, it's going to give us a very interesting curve. Now let's see what it does to our animation. So what you're looking at is the motion that we're getting from this animation curve. An interesting thing about spline curves is that they have a natural tendency to be curved. They want to be curved. That's what they're built to do. So let's show an example here of a ball keyframed at frame 0 to be a height of 0. And let's keyframe it at frame 10 to be at a height of 0. And keyframe it at frame 20 to be a height of 10. Now in our minds, we want this ball to remain at 0 from frame 0 to 10. And we want it to go up from 10 to 20. And as you can see in a graph editor, there's going to be a nice looking curve going from 0 to 10 and then 10 to 20. Now this is not what we want, but this is what's going to happen when you use a spline interpolation. And if we go back to our animation and play this animation, you can see that this ball is going to drop below 0 and then rise up. And that's not what we want. We want this ball to stay put on 0. So if we go to our graph editor, the way to fix that is to select those keys at frame 0 and frame 10 and flatten out the tangents. That'll give us a constant animation. That'll give us a constant flat curve going from 0 to 10. And then from 10 to 20, we're going to get a nice acceleration going up. Now that's the drawback of using spline interpolation, but that is very important to get very organic looking motion in 3D animation. Most character animation softwares will use spline interpolation by default. So you will get natural looking organic motion that is very arcing and that curves on you. You just have to be wary of times when you don't want it to be curved. Like for example, if you place a foot target on the ground, just like the example we used on the ball, we don't want that foot to go through the ground now, because the spline curve will want to dip down and come back up. So when using spline interpolation, as you should use it. Just be careful. Just keep in mind that you might have to flatten out tangents when you want them to be constant. So as you can see, using a Y translation is a very easy way to see what the graph editor can do. Now let's see what it does for X and Z. Pretty much for the X and Z translation, it does the same thing, but it goes along their axis. It goes along the X axis and it goes along the Z axis. We can think of it as a Y axis that's flipped on its side. So for X, an increase in value would be going in the positive X direction. A decrease in value would be going in the negative X direction. And the same thing for Z. Once you know the directions of the axes that you're working in, it's pretty easy. But one thing to keep in mind is that all of these axes are independent. So your Y curve has no effect on your X motion. And your X curve has no effect on your Z motion, and etc. So you can tug and pull on these keyframes all you want, and you can be sure that it won't affect the other axis. But what it will do is disorganize your animation. So be sure not to tug and pull in the horizontal direction too much, because that will readjust your key to a different point in time. You can do it up and downwards as much as you want, and that keeps your animation still pretty organized. Just be careful not to shift it off sideways too much, because it'll look like you have more keys than you really do. Now that we've looked at translation, let's look at scale. Let's hold off on rotation because that's a little more difficult. Scale is pretty easy. Instead of going up the units of translation, we're now going a percentage of scale. So we can go from 0 to 100 or 0 to 1,000 or whatever you want. It goes to infinite pretty much. So just like in translation, scaling in any one axis is independent to the other two axes. So scaling in Y has no effect in X or Z. I guess you're wondering what the importance is of scaling. Well, there's many different uses of scaling in animation. You can show squash and stretch, which is a very important principle in character animation. You can show expansion of like a balloon, or you can shrink an object very quickly to make it disappear. I use scaling a lot in Killer Bean Gunfire, where I would scale an object to 100 and then scale it back down to 0 2 frames later. It's much like turning a model on and off, but for example, in slow motion, you would want to see that gunfire grow in slow motion and then shrink in slow motion. And you wouldn't want to see it switch on and off in slow motion because it'll be too fast. Now let's talk about looking at rotational data in the graph editor. This is a whole different ballgame from looking at translational data or scaling data in the graph editor, because unlike translational and scaling, where the X, Y, and Z axes are independent of each other, in rotational data, the X, Y, and Z axes can all have a different part in orienting your object. So you can never really isolate the X, Y, and Z axes independently, at least not in the Euler coordinate system. Now there's three types of different rotational coordinate systems. We have the Euler coordinate system, which is the default system. It's basically X, Y, and Z, different rotations. You can rotate around the x-axis, y-axis, or z-axis. Now when I say rotate around, if we have the x-axis going across, you're going to be rotating around the axis, kind of like an axle, like an axle on a car, where the tire is rotating around this axle. So if we have y, you're going to be rotating around this way, and z, you're going to be rotating around this way. And the Euler coordinate system has X, Y, and Z. There's another system called the vector system. Now the vector system adds another axis. Not many 3D software has this vector system, but Animation Master has it. And the fourth axis is the roll axis, where you would have a bone and you could rotate it in X, Y, or Z, but then going down the bone, no matter which way the bone's oriented, you're going to have a perpendicular handle coming up, which is the roll handle. It's basically the twist of that bone. I like using vector a lot because it gives you extra control. Let's talk about the third rotational coordinate system, which is the quaternion system. It's pretty much the most advanced system, but I don't really use it that much because it's not really clear-cut how to read it in the graph editor. And the reason because is it introduces the W axis. So you have an X, Y, and Z axis plus the W axis. And the thing about the quaternion coordinates is it often prevents rotational flipping that you get from Euler rotations. Now, why is looking at rotational data difficult in the graph editor? Well, if you don't believe me, let's check one out. As you can see, this graph editor looks like a mess. It looks like spaghetti. You know, there's all these curves going around. Now, unlike translational and scaling data, it's not really obvious to the person what the rotations are doing. Now, if we look at this section where the curves are crisscrossing and going all over the place, there's not really a way to figure out what this rotation is going to look like in your head. Now, instead of trying to really figure out what the rotation is going to look like, it's best to really look at rotational curves in the most basic form, looking at it as a curve itself. So if we remember what translational curves were doing, if the slope is pretty steep, going up sharply or going down sharply, that means the rotation is going to happen very quickly. It's going to be a very snapping motion. And if that slope is pretty shallow, going down, or gradually going up, that means that rotation is going to happen slowly over a large amount of time. And if that curve is pretty flat, there's no slope or incline to it at all, that means that rotation is going to be held pretty constantly. So there's not going to be any animation going on there. Now that's really the only way you can look at a rotational curve, just looking at where it accelerates, where it decelerates, smoothing out little kinks from it, making sure the rotations are nice and smooth. One of the biggest problems in 3D animation is that you get a thing called gimbal lock. And gimbal lock happens when two rotational axes crisscross, and rotating in X and rotating in Z do the same thing. You're wondering, what? I don't get why they would crisscross. Well, if you've ever tried 3D animation and you tried rotating something in your animation, and you rotate it to a certain angle, like so, and then in another position you rotate it thinking that the way you rotated it is pretty much how it's going to look when it's animated. But when you go back and play your animation, it's rotating totally differently than what you expected. And this is because the way and order in which you rotate an object is not the same way and order the 3D software would rotate that object. In computer animation, in order to really rotate an object in a repeatable way, the 3D software uses what's called rotation order. Every software has a rotational order, but some of them won't let you change them. Now, what exactly is rotation order? Well, rotation orders mostly deal with the Euler coordinate system, where you have an X, Y, and Z axes, where you can rotate around those 3 axes. And the computer needs a way to rotate an object consistently, and the same way for every object. So it has to choose, which way should I rotate it? You might rotate an object, say you rotate it in Z and you like that position, and then you kind of roll it over this way, and then you rotate it this way, and you're like, that's a good rotation. That's what I want. Well, the computer doesn't keep track of all your little steps that you did to get to that rotation. It's going to rotate it the way it wants to, which is X, Y, or Z. It rotates in the X-axis first. Gets to that position where it's like, okay, matches yours in X, but I got to match it in the other 2 now. So it'll rotate in Y next, and it'll rotate in Z finally. Some software will let you change the rotational order. I recommend don't do this because it'll only confuse you much more. Stick to the default X, Y, and Z because rotations are hard enough to understand. Now let's describe what exactly happens in rotation orders and why gimbal lock happens. If we rotate X first, which is our first order of rotation, everything's fine. You know, you can rotate X independent of Y and Z because it's the first order of rotation. That's the first rotation that the computer is going to rotate. So if you don't touch Y and Z, you're totally fine. You can treat it like this is an independent rotation. Now if we add the Y rotation, you might not see this in your software. Some software will hide the fact that it has rotation orders, that the X and Z axes will crisscross. But picture this. If you rotate Y, since Y is the second degree of rotation, it's going to carry X along with it. So when you rotate in the Y-axis, the computer has to retain the X rotation. And the only way to do that is to make sure the X rotation doesn't change or move in relation to the Y rotation. So it will move with the Y rotation. But look at what happens when you rotate on the Y-axis too far. And watch the red circle crisscross with the blue circle. That's the X rotational axis crisscrossing with the Z rotational axis. Now if you rotate X or if you rotate Z, they both do the same thing. They both rotate your object in the same manner. This is where rotations get crazy. This is a problem, what we call a gimbal lock. And this is a big problem because if you were isolating X before, and if you goof up and rotate Z, now it's in 2 different axes. Now if you look at the graph editor, you're going to have an X curve and a Z curve doing the same thing, and that's going to give you wacky, wacky rotations. So if we do the Z, we can see that the Y-axis and the X-axis will rotate with the Z-axis because it's the last order of rotation. Order of rotation is something you don't really want to deal with, but it's good to understand because when you get flipping problems in your objects, when your objects don't rotate the way you want them to in between your keyframes, that's why it happens. Now when you see your rotation tool come up, you might not be seeing these different axes kind of crisscross. This is because you're not looking at the very local tool or very local rotation of that object. You're looking at a kind of global rotation for that entire object, but if you break it down into single individual rotations, you will see the X and Z axes cross. It's going to look like something that you're not very used to. Just be aware that this thing can happen, and this thing will screw you up. Now, how do you fix that problem if you have that problem? Well, like I said earlier, it's much more preferable to look at translational data than rotational data. So if you can, if you set your character up where it's constrained, and remember when I said you can constrain your head to look at a certain object by translating, or you could constrain your eyes to a locator and just translate it to rotate your eyes or your head or whatever else you want to rotate. That's a good way. That's a good start because now you don't have to deal with rotations. You're dealing with translations of this locator or whatever target. Another way to do it is by not using Euler coordinates. Euler will be tricky. You can use the other 2, which add another axis. It'll give you further control. However, the other axis, especially in vector coordinates, gives you another thing to animate, another thing to keep track of. Although I like the control. I like having more control than less control and having it whack out on you. Some software also has a filter that filters out this flipping problem, and it's called the Euler filter. Now, little disclaimer here. It's a misconception, especially in the whole industry, how to say Euler, how to say the word Euler. Or some people call it Euler, I call it Euler, I don't know. It looks like a Euler to me. Just pronounce it any way you want. I mean, we're animators. We're not supposed to be smart. Another way of dealing with these crazy rotations, say you do want to isolate rotations. Say you want an Olympic diver to do somersaults in the x-axis rotation, also while doing twisting rotations in y. Now, if you try to do that with a normal setup, if you try to do that with a Euler setup, because of rotation order, you will have problems. If you do want to isolate rotations in a Euler setup, the best way to do that is to have one bone for each rotation. Meaning, if I want to isolate x rotations, I would have a bone that can only rotate in the x-axis and lock off the y and z. Then if I wanted to isolate the y rotations, I would have another bone that can only rotate in y and lock off x and z. Now these isolation bones would then become the root, and your character resides under these bones. I see lots of cases where lots of beginner animators would encounter that kind of Euler flipping problem, but they really wouldn't understand why that's happening or how that's happening. So what they would do is now go in between their two keyframes and animate every single frame in between those two keyframes to force that rotation to do what they want it to do. Now this is a very bad way to animate, because not only does it make your animation less flexible if you need to change it, it's still not going to fix it down to the very minute level. If you go in between two frames with motion blur, in between those two frames, those curves still might flip out. Your motion blur is going to look crazy. Your motion blur might blur out for one frame, because in between two frames your object might flip to the extreme of one rotation, and that's pretty bad. So try to stay away from animating on every frame. We don't want to do that in computer animation. You got to let the computer animate for you. So if you run into a Euler problem where it's flipping or doing something, either filter it out with a Euler filter or figure out some way how to animate or to constrain your rotation so it does what you want it to do. A good way to isolate rotations, again, is using constraints. So you can always isolate a twisting rotation. In Animation Master, it's the aim roll at constraint, where you can control the twisting motion of a bone. Then you don't have to worry about flipping. Unfortunately, that setup has drawbacks also. Say you're working with the director and you have a spin in that twisting diving motion, and you're like, yeah, I think that spin, that's a good spin, it's pretty quick. And then you show it to the director, so you animate this locator going around the character just by translating now. Just translating that locator to control the spin, and you're done. Now think about how many keyframes I would take. At least 4 keyframes. One up here, then another keyframe here, it's going to rotate. Another keyframe down here, it's going to rotate. And another keyframe over here is going to rotate. So you get somewhat of a circle. If you want to rotate your guy about 5 times, that's 20 keyframes. So now you show your director, and the director's like, yeah, you know, I think that's cool, but I want him to spin at least, you know, what, 10 times. So now you're like, oh, okay, how would I do that? I got like 20 keys here. Now that's the problem. That's the problem of using translation instead of rotations. Now for that case, it might be best to do the isolating of rotations using more than one bone. So instead of animating 20 to 30 keyframes, you can set 2 keyframes. Set one at 0, and then if you want to do like 10 rotations, set another keyframe at 3,600 for 10 rotations of 360 degrees. In the graph editor, you get that really sharp line going from 0 to 3,600, and your guy's going to spin around 10 times. It's important to know different ways of doing things so you can make your life easier if you get changes. You know, if the director wants to change things on you, you got to be able, you got to make sure your shot is flexible enough that you can change things and that the first time you do things isn't the final way. So basically, the graph editor is the tool to see what your motion is doing in a visual representation. There's lots of times when I animate a few key poses where a guy might be shifting his weight just from landing from a strong land, and you might see that his weight shift is not really believable. So you would go in and you could figure out, okay, this curve for this weight shift has to decelerate. So right now it's not. It's kind of looking kind of bumpy. So I want to change these keyframes around to make this curve look like it's decelerating. That's one of the cases where graph editor is so important. You're going to live in a graph editor. You're going to love it. If you don't love it yet, you better love it because it's so powerful. So far we've just been talking about how to animate simple objects or objects with very few bones. Now let's talk about how to animate an entire character. What exactly is a keyframe? A keyframe is the basic building block of animation. However, in computer animation, it's very different to keyframe than in traditional animation or claymation. Unlike the traditional side, where you just set keys and you might have an assistant animator to set the in-between keys for you to draw out the in-betweens or interpolate what you're trying to do. In computer animation, the computer does that for you. Now, that's a good thing, and that's also a bad thing. The good thing is that it takes less people to do a production because the computer is assisting you in making the in-between keys. The bad thing is the computer is making the in-between keys. Now, what do I mean by that? In computer animation, if you set a keyframe in the beginning and in the end, it will definitely affect what's going on in the middle. In traditional animation, what goes on in the beginning and the end does not necessarily affect what's in the middle because they're independent of each other. A keyframe in the middle is pretty much independent from the beginning and the end. In computer animation, that's not the case because it's the computer trying to mathematically interpolate things for you. It's not a person saying, oh yeah, okay, I guess he wants to do this in the middle. No, the computer doesn't think, it just does it. In computer animation, when you set a keyframe for that selected object or a selected attribute, you're telling the computer to remember that pose or value for that current point in time. So the computer saves all that info into a database, and it's going to know how to interpolate between one keyframe at one point in time and another keyframe later in time. Different types of software will have two different basic types of keyframing. There's manual keyframing and there's auto keyframing. Manual keyframing is anytime you set a pose, anytime you rotate something or reposition something, you have to set a key for those attributes that you want to be keyed. Auto keyframing is anytime you rotate something or translate something, the computer will automatically set a key for you. Now, it depends on your preference on what you want to use because a lot of people like to use auto key simply because it's fast. You can skip that step of keyframing things. Some people like manual keying because they like to play around with poses a lot before they set the key. Personally, I like to auto key simply because it's fast, it doesn't distract you, you can animate, you can get into a flow. You don't have to stop every time and hit some key button or manually set a key. Now, going back to manually keying, there's different ways of manually keying your character. There's keying every single attribute that is keyable, which is sometimes crazy because you don't really want to key every single attribute. Sometimes things like visibility or IK enabling or things like that, you don't want to keyframe all the time. There's also a method of keying everything below the selected object. So you can select the shoulder and everything below the shoulder will be keyed all the way down to the fingertips. Or you can select the root and everything below the root will get keyed. Also, you can select an object and just have that object be keyed. So if you select the shoulder, you can just key the shoulder and nothing else below it or above it will be keyed. And the smallest form of manually keyframing is manually keyframing selected attributes. So if I select translate X for my root, I could just key that. Or if I select rotate Y for my leg or knee, that will just be keyed. Usually you'll do that for things like visibility or IK enabling, or for isolating rotations or translations. Now, what are the drawbacks of manually keying? Well, like I said earlier, manually keying, the biggest drawback is the amount of time it takes to manually key. That's another extra step you got to do every time you want to set a key. Now, if you like to manually key, if you set a manual key on the root, and you're going to key every single bone below that root, you have to worry about keying every single joint that you don't want to be keyed, like the fingers or toes or hair. Things that you want to go back and key later, you don't really want to manually key all the time, because then you have to go back and delete those keys eventually, or clean up those keys. Maybe you're saying, well, okay, I'm not going to go and key every single bone every time I make a key pose. I'm going to select the joints I want to be keyed and just key them for those joints. Now, that's also another extra step, selecting each joint that you want to be keyed, then manually setting that key. There are pros to manually keying. One thing is it helps you keep track of what's being keyed and what's not, because it forces you on every key pose to really think of what you're keying and what needs to be keyed. When you're auto keying, you're more in the flow of animation, and sometimes you don't realize that you should have keyed some bones and they're not being keyed, and later on you find out that a pose you make later on affects the poses that you made earlier, and you're like, whoa, I guess I should have keyed those. Now, what are some disadvantages of auto keying? Well, I mentioned some earlier where if you're animating and you're in a flow of animation using auto key, sometimes you might neglect some joints that need to be keyed. Also, if you're just rotating joints or translating in one axis using auto key, well, it might just key that one axis and leave the other two unkeyed. If you're using auto key and say you're just translating in X, auto key will not set keys for Y or Z. And you have to be aware of that, because if you set a key for Y or Z later on, that keyframe you did earlier with just X, the Y or Z will definitely be affected by the keyframe later on. Same goes for rotations. If you're having trouble on deciding which method to use, either manually keying or auto keying, it's best to really try it out for yourself. So try an animation with manually keying all the attributes and keyframes yourself, and try an animation using auto key. If you like manually keying, you'll find out that you probably won't use auto key at all. But if you like auto keying, you'll probably find out that maybe 25% of the time you will use manually key, because auto key cannot do everything, and sometimes auto key is slower than manually keying the entire body. I think it's best described in an example, because this might be a little bit confusing. First, let's introduce our character, and he's going to be our humanoid representative. First, let's think of an animation for him. Let's have him start from a squatting position, and then have him stand up and wave hi to everyone. So let's start with him squatting. I'm going to set keys for all the joints that need to be keyed for this squatting position. Basically, all the major joints in his body. We're going to skip the fingers. We're going to skip his hair. He doesn't have hair, so don't worry about that. Basically, I'm going to key his spine. I'm going to key his root, his hips. I'm going to key his legs. I'm going to key his arms and neck and head. So I'm going to position all of those bones into a squatting position, and then I'm ready to move on to my next keyframe. So my next keyframe, he's going to be standing up and maybe raising his arm a bit in the process of getting it up to wave. So again, I'm going to keyframe all the joints that I need to be keyed. Basically, they are the same keys. The hips, spine, neck, head, arms, legs. No fingers yet. Then we continue the keyframing for all the same joints in a standing position where his arm is up and it's ready to start waving. So we go to the next keyframe, and we're going to rotate it into the position of his arm waving just by rotating his arm. And then go ahead a few more frames and rotate the arm the other direction. Then do the same thing, a couple more keyframes, back and forth, and then we're done. And if we play our animation, we see our character standing up, and his arm is waving. Now let's bring another thing into the mix. Let's say we want him to squat back down after he waves. Well, okay, let's do this to our current animation. So after the last wave, we'll skip ahead a few more frames, and we're going to keyframe him into a squatting position again. And to do that, we would set keys for all the major joints again, the hips and so on, like we did before. Okay, now that we have that, let's scrub through our animation and let's check it out. And as you can see, the position he's in when he's waving is not the position we wanted him to be in. It looks pretty lame right now. It looks like, I don't know what it looks like. So that's the problem. Do you guys know why this happened? It's because we didn't set a key for those major joints while he was waving his arm. We were just setting keys for his arm. So here's an example of where you have to be aware of what he's going to be doing on the next keyframe, so you know on the current keyframe what joints to key. And as you can see, before my squatting pose, I want to be sure that in this standing pose where he stops waving, I want to be sure that all the joints that I want to key in the next pose are keyed in my current pose to hold that pose. Because otherwise, the keyframe on the next pose will affect my pose on this current frame. Okay? So to fix this mess up, well, it's going to be way too hard to just go back in the middle and just try to repose him into a standing position, because we had our standing position. It looked great before. So the easiest thing we could do is go to the keyframe where he's squatting, and what you can do is delete it if you think it's an easy pose to get back to, or you can cut that keyframe out for the entire frame. Now, cutting instead of deleting, what that will do is it will save the position or that pose into the clipboard of your computer. Every computer has a clipboard. It has nothing to do with the software. It has everything to do with your operating system. So all of that is shoved into memory in your computer, and you can go to that keyframe where he's last standing and waving and make sure you set all the keys for the major joints again, for the hips, the spine, neck, head, arms, legs. Now that we have that keyframe set, we can go to the frame where we wanted him to squat and just paste that pose back in there. And hopefully it should work with no problems. If you have a problem pasting that pose back in, well, most of the time you're going to have to just delete it and repose them. But this is a much easier way than fighting what this squatting key pose would do to your standing key pose. You might have noticed that our character is rising above the ground a little bit. This is because of our spline interpolation. To fix it, just go in your graph editor and flatten out the curves for his hips. Now he doesn't rise above the ground anymore. This brings up an important note in animation. When you do an animation and you think you're done, but you find out that you have to change something in the middle, it's really hard to change something in the middle while you have keyframes happening later on, because you're going to be fighting those keyframes on every single frame that you change in the middle. One thing you could do is to save off that chunk in the end into another file and delete that chunk from your main file. That way you can work in the middle section as if it is the end. So there are no other keyframes that are going to be fighting your posing in the middle. Another thing you can do, which is quite similar, is to save off your entire animation under a different name and then delete that last chunk and work on your middle section, which is no longer the middle, it's now the end. And then once you're done fixing it, then reload that entire piece and then copy the end chunk onto your current animation. So then it's a full, complete animation again. So to try to avoid changing things in the middle often, you should really play your animations through as you're making them. So everything in the beginning is to your liking before you move onwards. However, sometimes you may not have that luxury. Sometimes you might think your animation is complete and the director might say, oh no, I wanted this to happen in the middle. And then that sucks. Then you have to change it. You have no choice. Now going back to the animation, why didn't I want to keyframe the fingers yet? Well, because I really wasn't sure of what my animation was supposed to look like yet, or what I wanted it to look like for the entire body. So I wanted the entire body to look correct before I animate the fingers. Things like the fingers, the hair, the clothes, the tail, belly jiggles, or whatever, those things should come later. They should come after the major joints are all animated, because those things rely on the major joints. If you have to change the major joints and you animate the fingers already, most of the time you have to redo the fingers anyway. And fingers, like I said earlier, lots of joints, lots of things are key. So let's save them for later, because you never know when your major body animation will change. The director might say, no, I want him to, instead of running over here, I want him to run over here and jump. You know, and if you already have the fingers animated for your previous animation, all that stuff is lost. Just do the amount of work that you need to do, and you should have things signed off as you go. And with that said, it's another reason why you shouldn't really manually keyframe all the joints on every single pose, because that's keyframing those fingers also. I think with practice you'll like auto keying because it lets you be free in your creative expression. You don't have to be bogged down with, worrying about hitting that key button all the time. But that doesn't mean you'll never use manually keying. They both have their advantages, so definitely try out both and see which ones you like. Now we're going to talk about the second best tool in character animation, which is called the dope sheet. The dope sheet is like a spreadsheet for keyframes. It'll show you where your keyframes are for your selected object for the range of time that you want. Now let's go back to our hand waving animation and let's look at the keyframes in a dope sheet. As you can see when I get to the wave that I only have keys for the arm and no keys for the legs or the spine or the hips. And that's where I got that error when I brought them back down to a squatting position later on. So the dope sheet is a place where you can see which objects are keyed and where they're keyed, and if you need to key certain objects. Now probably the most important feature of the dope sheet is it allows you to retime your keyframes. So you can select a bunch of keyframes and you can slide them back and forwards. And this is great for making your animations quicker where you need them to be quicker by just sliding your keyframes closer together, or likewise spreading them out to make them slower. Now when using the dope sheet, it is very, very helpful to animate in a very organized manner. I like to animate on 3s and 4s. What that means is I set keys for all my major limbs every 3 frames or every 4 frames. What that does is it keeps my key poses very organized because I know I don't have keyframes in between every 3rd key pose or every 4th key pose. And if I need to retime my animations by stretching out key poses or compressing them, I could do it very easily in a dope sheet and not have to worry about messing up my animation whatsoever. Now I know it might be difficult to keep your key poses organized and looking like this up until the final product. Now this is by no means a rule you have to follow, but this is a method to help you animate more efficiently, because if you animate like this, it's so much easier to retime or to change. Let's go back to the hand waving animation to show an example of retiming. So on the squatting position in the beginning, let's say you want him to stand up much quicker than before. So we would take those key poses in the beginning and just shrink down the keyframes closer together, and let's see what the effect is. As you can see, he's standing up much quicker now. Now let's do the opposite. Let's take these keyframes and spread them apart. Of course, I need to be sure that I retain the same timing I have after he stands up, so that it doesn't change anything else. So I'm going to select the keyframes from the middle of the squat to the end of the animation so that I can be sure that the timing doesn't change for anything after he stands up. It's only going to change from the beginning of the squat to the stand-up position. Now the dope sheet is also useful for deleting big chunks of animation since it is a spreadsheet for keyframes. Now say I want my character to just stand up instead of standing up to wave high. I just want his arm to just remain motionless. So for all those keyframes I set for the arm waving, we could just delete those real quickly and watch what happens. So my character stands up and his arm's not moving. And I know it's not perfect, so we're going to have to go back to readjust anyways, but this is a good way to get rid of animations that you don't want. One thing more about the dope sheet, not only is it a spreadsheet for the keyframes on your joints, it's also a spreadsheet for the keyframes on individual attributes. So you can open up the selected joint in the dope sheet and you can see a list of all the attributes that are keyed and where the keyframes are. Now this is good if you want to check if the X, Y, or Z attributes are all keyed in the same key pose or if they're separated, things like that. I do recommend that all the X, Y, Z attributes are keyed together on that same keyframe. I don't recommend sliding around your X, Y, or Z attributes individually because in the dope sheet, once you close this attribute list, it's going to look like separate keyframes. So let's look at one keyframe where X, Y, and Z are keyed together, and let's shift X, Y, and Z separately. If we close this up again, it'll look like 3 different keyframes, and it's going to confuse you. So The key is be organized so things are easier, and don't shift around these attributes too much. They'll confuse you. Only shift them around when your animation is near final, and by shifting it, it makes it final, because you don't want to do this early on. It's going to confuse you too much, and it's going to make things a lot harder for you. Now, as we get more advanced, we can use the dope sheet to also layer animations. This is something I'm going to talk about later when we get into the art of animation. But keep in mind that we don't have to keep everything efficiently lined up like this. Once we get more into layering, and once we want to show more weight and follow through in animation, the dope sheet is a very easy place to do something like that, just by offsetting keys from these straight lines. If you layer your keyframes to look like this, that's a good way to show follow through and show weight in your character animation. I like the dope sheet. It's very easy to use, and it's very fast. And I hope you use the dope sheet, and I hope you learn how to use it, because without it, animation is not that fun. Trust me, the dope sheet makes things more fun. Now we're going to talk about the methods of posing in animation. There are really only two methods. There's a straight ahead posing method, and there's a pose to pose method. Straight ahead posing, you pretty much start from the beginning and you go every single frame all the way to the end. Meaning you pose the first keyframe, then maybe a frame or two later you continue that pose and pose the next one, and then a frame or two later continue onwards. So you have a flow. You don't really skip ahead. That's what pose to pose is. Pose to pose, you skip many frames ahead. So you pose at frame 1, and then maybe at frame 10 you do something else, like another extreme pose. And then maybe at frame 20 you do a totally different pose. There's advantages and disadvantages, of course, to both of these. Let's talk about the advantages of straight ahead posing. Now, like I said, straight ahead posing is you start at frame 1, then you go to frame 2, frame 3, frame 4, and so on. The advantages are it's totally creative, and you get spontaneity out of it, and things may happen that you didn't really plan for it to happen, but hey, you're animating it, the body's moving that way, and you know it's happening. So don't stop it. Let it flow. Let it, do its own thing. You get the creativity, you get the spontaneity and the fluidity in animations that you don't get in pose to pose, because pose to pose is very planned. It's very structured. And straight ahead it's very free flowing, and it's not planned. Okay, you may have an idea of what you want your character to do, but you don't really care what time this character does it or how he gets there. And that's what straight ahead is good at. Straight ahead is bad at planning a shot. If you want this character to hit a certain spot at a very specific time, straight ahead's not that good, because you might miss it, or you might hit it earlier than expected. There's not really any control until you reach that point in time. Okay? So straight ahead is very hard to use when working with live action backplates. Say a film studio shoots footage of people running around in a big mayhem, and this car explodes. Well, the director says, well, there's a CG monster running around chasing these guys, and he steps on the car. That's why it explodes. That's why I want the monster to step on this car at this exact moment in time. Well, if you're animating in straight ahead, it's really fun. You have your monster going all over the place, scaring the people, and then all of a sudden a car explodes, and your guy's like, you animated your monster like over here, and he's not even at that point yet. So that's the problem with straight ahead. The other problem with straight ahead is if you're working with a director, and the director says, okay, let me see what you're doing today. And pretty much you only animated the first 10 frames because you're doing straight ahead. And you're like, well, this is all I have so far. And the director's like, dude, 10 frames? What the hell? I expected, I wanted to see a basic blocking of the scene, I want to see what this character is supposed to be doing. Well, you can't do that with straight ahead, because straight ahead is, the first pass is usually the pass. First 2 passes, and that's it. You don't give much room to change or to do any fixes. Now, what are the advantages of pose to pose? Well, you could probably figure it out. Pose to pose is very organized. You start at frame 1, jump ahead to maybe frame 10 or frame 20, create a totally different pose, and fortunately the computer fills in the gap for us. It fills in frames between 1 and 10. Unfortunately, it might not do what we want it to do. So that's the drawback of pose to pose. Say you want your character to see a ball on the floor, pick up the ball, and throw the ball. Okay? In pose to pose, you would create a pose at frame 1 of the character standing, looking at the ball. Frame 10, the character might be squatting and touching the ball. Frame 20, the character would be standing and his arm would be back, ready to throw the ball. Frame 30, the character might be throwing the ball. That's your basic scene, and then you would go back to maybe frame 5 and adjust that pose to make it look like he's naturally squatting to pick up the ball. And then go to frame 15 and adjust that pose, and then going back to the in-betweens and just filling it in. Now, this is a very organized way to pose a character, to pose your animation. But as you can see, it's kind of mechanical. You laid out your extremes already, and now you're just going back and adjusting the in-betweens. You don't get that fluidity, you don't get that spontaneity that you did in straight ahead. Pose to pose is kind of boring. That's the drawback of it. It's very organized. You know, you can show the director that this is what I'm planning to do in this shot, and he can approve it or disapprove it, and it's very easy to change because you only keyed, like 4 keyframes? So it's good in that sense, and it's good in a sense where if you're working with a live action backplate, you can, time your animation exactly to the moment where you want the character to be. So like you can pose your character to smash that car at that exact point in time. The drawback of pose to pose is you're just animating motions, and you got to go back and adjust the middle keys between them, and sometimes you lose the life of your character in pose to pose. So now you're thinking, well, if straight ahead sucks and pose to pose sucks, then how do I animate? What kind of method should I use? Well, hey, the best method to use is a hybrid method. The hybrid method of using straight ahead animation and pose to pose animation. What that means is, instead of animating every single frame, 1, 2, 3, 4, 5, 6, or instead of skipping from frame 1 to frame 10 to frame 20, now we're going to animate maybe every 3 frames or every 4 frames. So now you get that advantage of free-flowing motion that you start from frame 1, and then maybe 3 frames later you're like, yeah, this guy's going to be in this motion. And then 3 frames after that he's going to be like in this motion, just keeping with the flow of the momentum of your character. But also that extra space in between. Say you keyframe at frame 1 and then you keyframe at frame 4. That extra space allows you to change things. So say the director says, okay, that animation looks good, but he's not reaching his mark. I want it to be a little longer here. So now you go in your dope sheet. You can look at your animation. It's separated by maybe 2 or 3 frames in between. Now you can shift those keys very easily. That's the hybrid method. It's very easy to edit, and you get that free-flowing animation going straight ahead. Now, the hybrid method, you still have to go back and adjust, but it's not like pose to pose where you go back in between and adjust the in-betweens. It's like working in layers. So first, you animate the major limbs, the major body motion. You leave out the stuff like the hair, or the fingers, or, the belly jiggle. Once all that major animation is done, and the director says, yeah, that's cool, it works out. Let's see the clothes now. Let's see how the clothes moves. Let's see how the fingers move, or his face. Then you go back in another layer, another pass of your animation. Work on the fingers for 1 pass. Go back again, work on the hair or the antennas, how they sway about in the 3rd pass. Then go back again, animate the belly jiggle or animate the clothes. Just keep going back and refining. That way, every time you go back, you're working on a different part of his body. And you're working on a straight ahead posing motion for that separate part. You're not working in a pose to pose fashion for the entire body. It's this way of working in layers that makes everything still free flowing, but it gives you the ability to change and to fix things, because when you show the director your full body animation of your major limbs, and if he doesn't like it, you change it. You don't lose any work. You don't lose the fingers or the antennas or anything else. And if he likes it, hey, that's done, you know? Go to the fingers, go to the next thing. So hybrid method is very cool, and this is pretty much the way that almost every CG animator animates in. Timing will affect the message that you are trying to portray in your animation. The time it takes for one frame to pass will make a big difference in your animation, especially if you're animating at 24 frames per second. I think it's best explained in an example. So let's take a look at this one. Okay, so we have a close-up of a person's head, and we're going to set 2 keyframes. We're going to set one keyframe to be looking straight forward, and we're going to set another one to be looking off to the side. Now let's set the first keyframe at frame 1 and set the next keyframe at frame 10. If we play this, it looks like the person is turning his head pretty slowly, as if to like just scan the room, pretty casual looking. Now let's go into our dope sheet and take these 2 keyframes, slide the one at frame 10 all the way down to frame 2. So now the 2 keyframes are right next to each other. So let's play our animation again. In an instant, the head goes from looking towards us to off to the left. And this is so incredibly fast that we can't really make any sense of it. This is almost mystical. It's like a magical thing. Maybe this guy's a ghost or something. Now let's go back to our dope sheet and separate the keyframes by 1 frame. So the first keyframe is at frame 1, and the second keyframe is at frame 3. Going back to our animation, his head is moving very quickly, as if he was hit by an extreme force. Maybe he got shot. Let's go back to our dope sheet and move the keyframes further apart. Let's make the second keyframe at frame 3 or 4, and now these keys are about 2 to 3 frames apart. Go back to our animation, and his head is snapping pretty quickly again, but not as much as before. So maybe this time it seems like the guy got punched in the face rather than shot in the head. Okay, now let's go back to our dope sheet and separate the keyframes by maybe 4 or 5 frames apart. And we go back to our animation. Now the head turns relatively quickly. He's not really struck by anything. He's looking as if he's surprised, or something startled him off to the side, and he's looking to see what it is. So before we go back to separate these keyframes even more, let's go in our graph editor, and we can see it's a constant line. Now let's make these tangents flat. So there's acceleration and deceleration. Now what this does is, if you look at the slope, it's now a lot steeper than before. So the action is going to be quicker than before. But we'll have some ease up and ease down action. And going back to our animation, yes, it does look quicker, and it seems more natural. I like to definitely flatten my tangents out for the beginning and ends of my animation. It happens normally in between because the spline curve naturally smooths out by itself. But towards the end, the very last keyframe, usually it just truncates off. And if you want to ease out, definitely flatten out your curves at the very end of your animation. Okay, let's go back to our dope sheet and separate these 2 keyframes by maybe 6 to 8 frames. And going back to our animation, now the guy is more relaxed. He's turning his head, he's looking off to the side, and nothing much is going on, you know, no big deal. Okay, now let's separate the keys by about 12 to 15 frames apart. As you can see, he's turning his head pretty slowly. Maybe he's like sinister. Maybe he's giving you the evil eye. This guy is serious. So now you see what timing is about. Your message can change depending on how far apart your keyframes are and how quick the actions are. Now keep in mind, this does change with scale. So if you're a little mouse, your legs would be moving a lot quicker than a person would. If you're a spider, your legs would move quicker than a mouse would. So if you go bigger now, if you're an elephant, you would move slower than a human would. Now keep in mind, this is because that the limbs need to be moving a lot more mass than before. A mouse is very light, so he can move very quickly, and you know, his legs can handle it. An elephant needs to move a lot of mass. Timing can also affect the style of your animation. Lots of times when you animate in a very realistic human motion, lots of times it's pretty slow. If you see a lot of motion capture in computer games, you'll notice that, hey, these guys are moving pretty slow for what they look like. If you make the timing of your keyframes to be a lot sharper, a lot quicker, it's much more stylized now. It'd be a lot more cartoon-like. That might be what you want, and it might not be. Timing is something you'll get with experience. It's very hard for me to tell you exactly how long one frame takes. You just have to do it a lot. I like to animate on 3s and 4s, meaning I like to key every 3 frames or every 4 frames. Like I said before, it gives me the ability to change my timing in the dope sheet very easily. And it also lets me keep in a groove when I'm animating. I'm not worried about what happens 10 frames from now. I'm worried about what happens 3 frames from now. So it's a lot more current. You're more focused on the momentum of maybe some limbs or the weight moving forward, things like that. Also, one thing to keep in mind is that there's a big difference between 30 frames per second and 24 frames per second. If you're going to animate for a film, you should definitely do it at 24 frames per second. If you're going to animate for video or maybe computer games, you should do it at 30 frames per second. When I started learning how to animate, I animated at 30 frames per second because everything I did went to tape. And when I started working on feature films, I found out that my animation at 24, what I would usually do at 30, it looks too slow, and I ended up shifting all the keys in a dope sheet to be closer together. So, just keep that in mind. It won't be a big change. It won't be a difficult transition going from one to the other, but, it's going to take maybe a day to get used to, and you'll be right there. Okay, now that you know the basics of animation and how to really go from one keyframe to the next, let's talk about how to make your animations look good, how to make the motions look natural and more believable.